Hello, welcome to Shidiwa. Can I take your order? In this video, I'm going to be explaining current division, and it's a trap, as Admiral Akbar would say. It's very similar to voltage division, only, well, you only use current division when you have resistors in parallel. Whoopsie! You don't ever use current division when you have resistors in series. That's for voltage division. So yes, in series the current is going to be the same. In parallel the voltage is going to be the same, as I've probably explained 3 times now. So this is the only case where you use current division, not this case. You may be wondering what the trap is. Well, I'm glad you're wondering. Right, so a basic example. Okay, just as a pre-note, I've always been using a voltage source to indicate our power supply so far, but for the sake of simplicity, I'm going to say there's a current source in this example. Now, a current source just supplies current, and a voltage source just supplies voltage. Power is related by the equation current times voltage, and it basically represents I guess the force, or the electric forceness of, well, really the amount of energy that's contained within the circuit. Okay, so clear all that. We have, I keep doing it out of habit, but say we have a current source, and it's an ideal current source of 5 amps. An ideal current source just means it'll pump out as much energy as required to keep that 5 amps flowing from there to there. And say we have 2 resistors in parallel. Now, we know that there's 5 amps going in here, and this 5 amps is going to be split into 2 streams, and then it's going to join back up into 5 amps going along here. Now, just as a special little trick, if you see 2 resistors that have the exact same value, and you know the current going in, because they're the same value, they're going to be split up evenly. The flow of this path is going to be the same as the flow in this path. That's just something to note. So we can already say that in each one it's going to be 2.5 amps, which is of course 5 over 2, equals 2.5. But say we wanted to do it using the current division formula. The current division formula is a lot like the voltage division formula, only, as again, it's a trap. And I'll explain it. I equals, okay, so I is the current along this mesh, or branch, or path place. The current along here is going to equal the total current, I tot, times the resistor opposite to the branch you're trying to find the current along. So if we were because it's this current, we want to take the value of this resistor. If we were trying to find the current along here, we would want to take the value of the opposite resistor, and that's the key difference between voltage division and current division. With current division, you're doing the opposite resistor. With voltage division, you're doing the same resistor. And of course, this is over R1 plus R2. So in this case, our amperage is I tot, which is 5 volts in total, times our opposite resistor, and it's the same thing, which is why it splits evenly, I guess, over 2 plus 2, or R1 plus R2. So this is going to be 5 times 2 over 4 equals 10 over 4 equals 2.5. And would you look at that, because we knew that special trick, we could already do it. So now I'm going to do another example, which will hopefully be more stimulating. Say we have 7 amps, and a resistor of 3, and a resistor of 10. Now, let me ask you a question. Which branch is going to have more current flowing through it? Ding, 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 ding. Time's over! Okay, it's going to be this branch, because we have least resistance over here. Therefore, there's going to be more current wanting to flow through here. Whereas this branch has got 10 ohms of resistance. So there's hardly going to be any flowing through, well, not as much. It's going to be less than a third. So you can sort of see that the current is going to be dividing proportional to the resistance. There's going to be more current flowing through here because there's less resistance. It's just like if you had a pipe and you had a really, really small one, or a small pipe here, which would make more resistance, and a big pipe here, which would make less resistance. More of the current is going to flow through the one with 3 in it than the one with 10. And yeah, that's something you can hopefully see with a bit of practice. So again, using our current division formula, let's say we want to find the current along this 3 ohm. We'll call this I question mark. The current in question is going to be the total current, which is 7. Actually, I'll write out all the notations first. It's going to be I tot times R opposite over R1 plus R2. And of course that's 7. Our total current is 7 times the opposite resistor, which is 10. And you've got to remember it's the opposite. I am emphasizing a bit, but hopefully it's for the better. And 10 over 3 plus 10 is 13, which is R1 plus R2. And subbing that in the calculator would give 70 over 13, or 5.3846 amps. So we know there's about 5.3 amps flowing through here. We know there's 7 amps flowing in here, using something called Kirchhoff's current law, which I'll do in a later video. But we know the total amounts flowing through here is going to be split into 5.3 and some other unknown quantity. But that unknown quantity has to come back here and go back to 7 amps. So to get this value quickly, we'd just go 7 minus 5.3, and that would give us 1.6. We could use the current division formula, but hopefully you could probably do that on your own. In fact, if I set that up for you, you'd get the total current, which is 7, times R opposite. Remember, R opposite in this case is 3 over R1, which is 3 plus 10 over 13, and that would hopefully give us the same answer. I'll just check right now, and correct. Excellent. So that's how current division works. Now, something even more tricky. I've introduced this current source just for this example. However, we could still use a voltage source. It would just require a bit extra calculation. So, say we had a voltage source with 5 volts. Now, say we were asked to find the current along here, I question mark, where this resistor was 3, this resistor was 2. Draw that a bit neater. The first thing you'd want to find is, what is this current through here? Well, if you remember when we were combining resistors, we know that the equivalent resistor, this circuit can be redrawn to an equivalent circuit with just one resistor, where the equivalent resistor, Req, is equal to R1 times R2 over R1 plus R2, which is equal to 3 times 2 over 3 plus 2 equals 6 over 5 equals 1.2. So, now that we have the resistance of our equivalent circuit, we can find the current of our equivalent circuit, which would be, if I just label this little circle, that's this circle here. So the current's going to be the same in both those circuits. So using Ohm's law, I equals V on R, we can see that that's going to be 5 for the total voltage over 1.2 for the equivalent resistance, and that's going to give us 4.16 recurring. So that's our I total value, equals 4.16. Now, to get to use our current division formula, it's exactly the same as if this was a current source. I in question equals I total times resistance opposite over resistor 1 plus resistor 2, and that's 4.16 recurring, times our resistor opposite is 2 divided by 3 plus 2, and if you smack that into a calculator, you should get 1.6 recurring. I hope you've enjoyed this video, and even more, I hope you've learnt something. Thanks for watching, and as always, see you again later.